My name is Zach Thomas, and this is my vocabulary project. So the first step of this project is to create a matrix that is not invertible and has a rank of 3, as well as the other parameters shown from the prompt, and this is the matrix that I came up with. The next step is to find the basis for the column space of A. This is done by reducing the initial matrix into REF, which is shown on the left. So when this matrix is reduced to REF, there are 3 pivotal columns, those being columns 1, 2, and 4. So in order to find the basis for the column space, you look at the 3 pivotal columns, those being 1, 2, and 4, and you go back to the initial matrix, and columns 1, 2, and 4 from the initial matrix are the basis for the column space. So you can see that on the right. And the geometrically, the column space is a 3D hyperplane in R5. So after calculating the column space, you then calculate the basis for the null space. So for column space, you only reduce to REF, but for null space, you reduce to RREF, which is shown at the top. And then after this, you make this matrix into a set of equations, which is shown below that. And then you parameterize these equations, which is shown to the right of that. So because there are 2 parameters, those being A and B, that means that geometrically the null space is a 2D hyperplane, which is a line, and it's still in R5. So the steps for going from the equations to the matrix equation is you pull the coefficients from A in each of these equations, and then that's what's multiplied by x3, and then you pull the coefficients from B, and that's what's multiplied by x5. So the basis for the null space is the first column being 1, -2, 1, 0, 0, and the last column being -30, -20, 0, -10, and 1. And that is from pulling the coefficients from x3 and x5 from the matrix equation shown. And an easy way to remember it is the number of parameters is the dimension, and the number of columns in the basis for the null space. So next, because the determinant of the initial matrix is 0, the columns do not form a linearly independent set, and this will be described more on the next slide about big theorem. So because the columns don't form a linearly independent set, that means that if the matrix was represented as a linear transformation, it would not be 1-to-1. And because the column space is a 3D hyperplane in R5, the range does not cover the entire codomain, so the representation of the linear matrix is not onto. So it's not onto, and it's not 1-to-1. So here's the big theorem of linear algebra, and it basically says that if matrix A is invertible, then the rest of these statements must be the case. But my matrix is not invertible, so that means that the opposite of all these statements are the case. So the 4 I picked are rank, nullity, determinant, and the columns being linearly dependent. So the rank of my matrix is not n, and I know this because the rank of the matrix is 3. So n would be the number of columns or rows in the matrix. And the next statement is that the nullity of the matrix is not 0. And I know this because rank plus nullity equals the number of columns or rows. And because my rank is 3, that means that the nullity must be 2, because 3 plus 2 equals 5. Next, the determinant of my matrix is 0. And lastly, the columns of A form a linearly dependent set. All of these statements are known because the big theorem of linear algebra says that if A is not invertible, then that means that these statements must be true.